Hey guys, Dr. Kruse here. Elementary statistics. We're going to talk about hypothesis testing, how to set up a hypothesis test for the difference of two proportions. A proportion is kind of like a fraction, what fraction of people did this and what fraction of people did that. I'm going to be using the critical region or the traditional method. All right, so just for example, is the proportion, think fraction. Anytime you see a proportion, like 4 out of 5 people did this or 7 out of 9 people did that, is the proportion of people who are Democrats in Oklahoma significantly different from the proportion of people who are Democrats in Nebraska? So you're kind of comparing two populations. You're comparing a proportion of that population. So this is the Oklahoma proportion of Democrats versus the Nebraska proportion of Democrats. All right, this is the kind of problem that we'll be working with. We're going to test a fraction in one group and compare it to a fraction in another group. We're going to see the difference between the two fractions, the two proportions, and we're going to see if it's significantly different. If it's just a little bit different, nobody cares, but if it's significantly different, then people care. All right, now before we get started, I want to remind you that we're going to be using a level of significance of 5%. Alpha is 5%. And we're going to be using the z-table today with these proportions. So let me remind you that if you have a left-tailed test, if they say population 1 or proportion 1 is less than proportion 2, that's a left-tailed test. And if we're using 5%, we need to figure out what z number to start coloring to the left. If we want 5% of the area here in the shaded area and 95% on the right, I need to draw this line at the z number that leaves 5% to the left. And there's several ways to do it. Most people just use a table. All right, so grabbing my table here, and if I want 5% of the curve shaded to the left, I got to look for 5% here in the table. And it's going to be right here halfway between these two numbers here. So far the z number is negative 1.6. And then if I go up from this number, it would be 1.64. or 1.65. Now it's halfway in between, so we're going to split the difference and say it's negative 1.645. All right, another way to do it is maybe you have this handy table right here where it tells you if you have a level of significance, alpha, of 5%, and you're doing a left-tailed test, they're going to tell you to start shading 1.6 steps to the left. Here's a right-tailed test. Here's a two-tailed test. I'll show you those in just a second. So there's another way. If you have this handy-dandy chart, you have the 5% places to start shading, and you have the 1% places to start shading. And then finally, some people just like to do it on their calculator. So you're going to tell your calculator that the area to the left that you want to shade is 5%, and the calculator will work backwards and tell you what that z number is that produced an area of 5%. So grab your calculator there, and what you're looking for is in the distribution right there, distribution, so second function, distribution, and I want what's called the backwards normal distribution. It's inverse. Inverse means backwards. So we're doing a normal distribution curve, that means z, and I'm working it backwards. I'm going to tell them the area, and they're going to work it backwards and tell me what the z number is. So I choose that, and I just want 5%. Mu is always 0. That's my z number in the middle. Remember, we go 0, 1, 2, 3 to the right, and negative 1, negative 2, negative 3 to the left. So our population average is 0, give or take 1. That's our standard deviation of 1. All right, our standard normal curve. Just leave those at 0 and 1 and put in the area that you need. So we need 5% to the left, and you can just enter, 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 paste it into your calculation window, hit enter one more time to calculate, and it says negative 1.645 to the left is where you start coloring. So here's 0, there's 1 step to the left, there's 2 steps to the left, here's about 1.5 steps to the left, so a little bit further than 1.5 steps to the left. That's where you draw the line, that's where you start shading for 5%. All right, and then the others that we're going to use today real quick. A right-tailed test works the same way. If you're on your calculator, you would look up 95%. You'd do inverse normal 95%, and it would tell you, well, this time start coloring 1.6 steps to the right. 0, 1, and a little more than half a step to the right. Shades 5% to the right. And it's also in the table. And then your two-tailed test, if our challenge is the proportion 1 is not equal to proportion 2, that's a two-tailed test. We don't know if it's lower, we don't know if it's higher. So we split the 5% in half. Half of 5% is 2.5%. So 2.5% here and 2.5% there. And we looked this up in the table. If you're using your calculator, you want to put in 0.025. Move that decimal 2 to the left and tell them you want an area of 0.025, and it will tell you the z number for that area is negative 1.96. And then over here on the other side is its positive twin. That gives us 2.5% left and 2.5% right. That's 5%, and the other 95% is in the middle. So those are the z numbers we're going to be using today. So we need to go over some terms and definitions. I've got 3 problems I want to work, but we kind of need to go over some definitions and maybe some symbols you haven't seen before. So I just made up some information here. There used to be a commercial that said 4 out of 5 dentists prefer Crest. All right, so I just changed the numbers and I said 43 out of 51 dentists, and let's say population 1 is Oklahoma. So dentists in Oklahoma prefer Crest. And maybe in Nebraska, 42 out of 53 prefer Crest. All right, so I'm going to look at those fractions. 43 out of 51, that's a fraction, that's a proportion. And 42 out of 53, that's a fraction, that's a proportion. I'm going to compare those two proportions and see if they're significantly different. See if one's significantly lower than or greater than or just not equal to the second population. We call the first number here the number of successes. We call that R. And then N, you already know, that's how many people you sampled, 51 dentists and 53 dentists. All right, so R is the first number, the number of successes out of the number of people you sampled. Now our population numbers, remember, we just never really know those, all right? We're never really going to know, we're not going to be able to ask all the dentists in Oklahoma, all right? That would be the population proportion. Out of every single dentist in Oklahoma, how many prefer Crest? Well, we're never really going to know that number. All right, so this is something that we usually don't know. And remember, Q is the population of, or the probability of failure. So if I say that 70% like Crest, then 30% would not like Crest. That'd be the rest of the 100%. All right, so that's unknown. We're not really going to use Q today. We're going to use P. We're kind of guessing at the population proportion. All right, P for proportion, P for population, however you want to think about it. We're going to guess at the population proportion by taking a sample, and that's what P hat and Q hat are. That's our actual sample. That's the dentist that we were able to get a hold of. We can't get a hold of every dentist in Oklahoma, and we can't get a hold of every dentist in Nebraska. That would be population numbers. But I can get a hold of 51 dentists in Oklahoma and 53 dentists in Nebraska. That's my sample. So I'm going to guess at the population based on the dentists that I sampled. All right, P hat, that's just my sample fraction. All right, it's my sample fraction of success, sample probability of success, sample proportion of success. It's just the 43 out of 51. Out of 51 dentists in Oklahoma, 43 we're going to call Crest success. 43 out of 51 were success. Now 43 out of 51 is the exact number. You can change it to a decimal. It just depends on how you want to calculate it. Most of the time, if you want to change it to a decimal and use 4 numbers after the decimal place, so 4 decimal places, you can use 0.8431, and usually that's going to get you the right answer. Most of the time, if you go 4 decimal places, that'll get you the right answer. But if you want to be a little more exact, well, you can put in all of these decimals. That'll get you a little closer. And if you want to be super exact, well, you can just use this fraction instead of the decimal. All right, I'm going to use 4 decimal places just because it kind of takes up less room. All right, but it's up to you what you use. Use 4 decimal places, use 10 decimal places, use the fraction. The fraction is the most accurate. It just depends on what you want to use. Q hat, all right, that's the probability of failure. So this is our proportion of success, and the rest of it is my proportion of failure. So if 43 dentists liked Crest, that means that 8 dentists did not like Crest. Just 51 minus 43 gives you 8. So you can use the fraction if you want to be exact, or you can just change it to the 10-digit decimal and use 4 digits of it. So 0.1569 is what I'm going to use. Easier way to find Q hat is just do 1 minus P hat. All right, so it looks like 84% of dentists prefer Crest. Well, 100% minus 84% leaves about 16%, so that kind of makes sense. Lots of people just do it this way. It's quicker. All right, and then finally, p-bar. P-bar, this is kind of our standard deviation calculation. You guys remember we take a sample for group 1 and a sample for group 2. We find the difference between them, and then we divide by the standard deviation. But the standard deviation always gets adjusted, and for proportions, we need to use what's called p-bar and q-bar for our standard deviation adjustment, the thing that we're going to divide by. All right, it's called a pooled estimate, and pooled just means you throw everybody in the same pool. You kind of pool everybody together. So what we're going to do is we're going to add up all the successes on top. All right, my successes were 43 and 42. I'm going to add those together on top. All right, and then you add up the total number of samples on bottom. So 43 plus 42 on top, and then I had 51 dentists and 53 dentists on bottom. So you add the R's, you're going to pool them together, and you're going to add the N's, you're going to pool them together. And this comes up with a new fraction. All right, it's kind of a combined fraction. Again, you can use the fraction if you want to be perfectly accurate, or you can change it to a decimal, and I'm going to use 0.8173. Now remember, q-bar would be the rest of it. All right, this is the pooled estimate of success. This is kind of the pooled estimate of failure, but the easy way to calculate Q is just take P away from 1. All right, so it looks like P was about 82% for this. 100% minus 82% is about 18%. That makes sense. So the easy way is just 1 minus whatever P-bar was. Technically, if this was 85 out of 104, that means there's 19 left. 104 minus 85 is 19. So 19 out of 104 is the exact fraction. Here's the decimal. I'm going to use 0.1827. All right, and then finally, the formula that we're going to use, this is our test statistic. This tells us whether we can reject the null hypothesis or we have to accept the null hypothesis. We have to see where this number lands by plugging in all that information up above. All right, so I'm not actually going to work this problem. That was just a nice, easy kind of way to explain the different parts that we're going to need to work with. So R out of N, that's 43 out of 51 or 42 out of 53. There's our two groups. Population proportion, we're never really going to know. We're trying to guess at it with our sample information, and that's the proportion of success and the proportion of failure. And then finally, to calculate our adjustment for standard deviation, we're going to have to calculate what's called a p-bar, a pooled estimate, where we kind of total the successes together and total the numbers together and get kind of a new fraction to divide by on the bottom. All right, let's work 3 problems here. This is the first one. Would you favor spending more federal tax money on the arts? Of a random sample of group 1, the number is 95. Of a random sample of 95 politically conservative voters, 19 of them responded yes. So there's our fraction for group 1, 19 successes out of 95 that were surveyed. Another random sample of group 2, the number in group 2 is 85. Another random sample of 85 politically moderate voters showed that 21 responded yes. So this is going to be 21 out of 85 is our proportion for group 2, R divided by N. Does this information indicate that the population proportion of conservative voters inclined to spend more federal tax money on funding the arts is less than, there we go, that's our test right there, the proportion of moderate voters so inclined, and we want a level of significance of 5%. So first things first, let's get this thing organized. Group 1, you need to title it, you need to give it a name. That's the conservative voters who said yes. And then group 2, that was our moderate voters that said yes. And then in between them, I like to put a symbol about which way we're going with this test. Are we saying these guys are lower? Are we saying these guys are lower? Or are we just saying they're different? All right, and we got to read carefully here because look, they're trying to kind of trick you here. Inclined to spend more, that kind of makes me feel like that's going to be a greater than symbol, but you have to read. All right, you got to read carefully. This is all just an adjective for these voters here. Voters, they're conservative voters. They're the voters that are inclined to spend more on the arts. That's just adjectives describing voters. So don't let this trick you over here. is less than is the actual test. So conservative is less than moderate. You got to kind of take out all the adjectives and all the extra words and get it down to what is my test. Conservative is less than moderate. All right, let's just organize the information here. Okay, so conservative, there was 19 out of 95. That's R out of N, group 1. This is extra information, but I like to write it down. My population proportion for group 1 is unknown, all right? I'll never be able to ask all politically conservative voters this question. I just won't be able to get around to all of them. So I'm not going to know what the true proportion is. All I can do is guess at it using the ones that I could catch, using the 95 senators or voters that I could catch. So I'm going to guess at the population based on my sample. So my sample was 19 successes out of 95. 19 said yes out of 95 that I asked. Now that's a really nice decimal. That's 0.2. I'm definitely going to use that. And then Q hat is just the rest of them. So if 19 said yes, 76 said no. That's 0.8. Notice it adds up to 1. So does the fraction. Over here, group 2, 21 out of 85. So R divided by N, that's 21 out of 85. Again, the true population proportion for group 2 is unknown. I won't be able to find all the moderate voters and ask them this question. All I could find was 85, all right? So the true population proportion of people who answer this question the way I want them to is unknown. We'll never know it. We're going to guess at it with our sample, and our sample said 21 out of 85. Which is this decimal. I'm going to use 0.2471. If you want to be super exact, use the fraction. All right. You can kind of be medium exact if you use all these 10 digits here. All right. So my advice is start with 4 decimal places, and if that doesn't quite get you the right answer, then maybe use some more decimal places or actually use the exact fraction in your calculations. It's just how exact do you want to be, do you need to be? Usually 4 numbers after the decimal will get you the right answer. All right, Q hat's the rest of them. So if 21 said yes, then 64 said no. And that's this decimal right here. All right, now here's our P bar, Q bar calculation. This is our pooled estimate. We're going to pool the 19 and 21 together. All the people that said yes. So I'm going to pool my yeses together. 19 plus 21, that's 40. And I'm going to pool my numbers together, 95 in this group, 85 in that group. I'm going to pool them together for 180, which gives us a new fraction and a new decimal. All right. So this is the pooled proportion of success. The pooled proportion of success, if I pooled them together, it's about 22%, which means about 78% are failure. The easiest way to do it is 1 minus whatever P bar was, 1 minus P bar. If 40 said yes, that means 140 said no. Out of 180, that's my 0.7 repeating. I'm going to use 0.7778. That 7's going to round that one up to 8. All right. Step 1, let's set up our hypothesis. We saw that up above. We're going to say this population proportion, the true population proportion that we don't know, that we're kind of guessing at, we're going to say this one is less than this one. Even though we don't know what those are, we're going to kind of guess at it and test this based on our samples. All right, so the null hypothesis, H null, H0, says that these two populations are exactly the same. All right, and that's their claim. We're going to challenge it. This is the alternate hypothesis. This is our challenge to their claim. This is like the accepted belief, oh, both groups are going to vote the same. All right, it's not really that big a deal. That's what they're saying. That's the accepted belief. That's their advertised claim. We're going to challenge that claim. We're either going to say this is not true, it's less than, or greater than, or not equal to. We're going to challenge the claim that they're the same. So the null hypothesis says they're the same. When you're comparing two groups or two proportions, it's always going to say the two groups are the same. And you're going to say, no, they're not. That's your challenge. You just got to figure out how to phrase your symbol there. Step 2, I like to draw a picture. All right, so we're talking about a 5% alpha level of significance to the left. Less than means left tail. You're going to shade the left tail, and we already talked about the Z number where we start coloring is 1.6 steps negative. So here's 0, 1 step to the left, 1.5, a little more, that's about 1.6 steps negative. Shade to the left, that puts 5% here and 95% here. Now pretend you don't see the dot here. This is the result of our test. We haven't run the test yet. That's step 3 for me. So using my formula, this is my test statistic, my Z star. Whatever this works out to be, I'm going to place it on the axis and see if it landed in the 95% area or the 5% area. If it lands here, I kind of win. I get to reject what they said. I get to reject the null hypothesis. If it lands here, I get to say, aha, I was right. All right. These are not the same. Group 1 is less than group 2. Proportion 1 is less than proportion 2. And of course, they're different. All right, look at our proportions. Here's proportion group 1 from our sample is 0.2. Proportion group 2 is 0.24 or 25 if you round it. This is 0.2, that's 0.25. Yeah, they're different. They're never going to be exactly the same, but are they different enough that anybody cares? That's our question. Are they significantly different? That's what we're trying to figure out. That's why we run the test, to see if they're significantly different. If our test lands anywhere here in the 95%, there's no big difference. There's not a significant difference. All right. If it lands over here, we can say, oh, there is a significant difference. These groups are way, way, way far apart. I reject what you said. All right. Our test, when you run all the numbers through, you guys have all the numbers up above. So I used 4 decimal places, 4 numbers after the decimal. Round the last one there if you have to. Looks like this. Do the calculation. I end up with negative 0.7590. All right, 0.75, that's 3/4. That's 3/4 of a step to the negative, 3/4 of a step to the left. Here's 1 whole step to the left. I don't want to go that far. I want to go about 3/4 of the way. So my test dot lands right about there, which is clearly in the 95% region. So I lose this one. I have to accept what they said. They said the populations are the same. They're saying they're not that different, and I have to accept that. All right. I tried to prove that they were different. My test didn't land in the right spot. So over here I lose. I have to say, okay, you were right. I accept what you said, except we have to say it the hard way. And instead of saying accept the null hypothesis, I have to say, well, I failed to reject the null hypothesis, because that's what we were trying to do. We were trying to reject their claim. We're trying to reject what they said, and we failed. All right, our test dot didn't land in the right place, so we failed to reject what they said, their claim. Here's how you phrase it. I just always write it the same way every time. There is not enough evidence. Remember, we failed. I tried to reject what they said and I failed. That means I did not have enough evidence. There is not enough evidence at the 5% level of significance to conclude that. So those words are the same almost every time for me. And then the rest of it is just restate that challenge that failed. Your challenge was the population proportion of conservative voters, and this is all adjectives, who are inclined to spend more federal tax money on funding the arts, is less than, there's my challenge, the proportion of moderate voters, same thing, so inclined. All right. So what I'm saying is I did not have enough evidence to prove my challenge. My challenge was that group 1 was less than group 2. I don't have enough evidence to prove that. I failed to reject what you said. I was trying to, but I failed. Now, if I cover up, fail to, let's say it turned out the other way, and if I reject, the only word I'm going to change is I'm going to erase not. That's the only word I would change. So if it turns out that I can reject the null hypothesis, I would just say there is enough evidence. All right, so know the difference. There's really only one word difference in your interpretation. This is your conclusion, this is your interpretation, and the only word that's going to change in your interpretation is or is not. So try and keep those straight. All right, let's do a couple more real quick. Do you prefer paintings in which the people are fully clothed? Kind of a weird question. This question was asked by a professional survey group on behalf of a national arts organization. A random sample of 56, group 1, the number in group 1, 56 people who are conservative voters, that's our first group, conservative, showed that 43 of them said yes. So conservative, you can say conservative yes if you want to. So 43 out of 56 is going to be my first fraction, my first proportion. Another sample, group 2, that had 62 people in it, said that 36 said yes. So 36 out of 62 is my second group. Does this indicate that the population proportion of conservatives is higher, and then liberals? All right, this part's assumed. Conservative is higher than what? Well, higher than the other group, higher than liberals. Okay, again, true numbers, the true proportion, the true population proportion is unknown. We're going to guess at it by you looking at our samples. So p hat is my sample of success, 43 out of 56, this decimal. All right, were conservatives that said yes. And then q hat is the ones that said no. 43 said yes, 13 said no for these two decimals here. Liberals, the number that said yes was 36 out of 62. That's my liberal proportion of success, this decimal here. Failure is just 1 minus that, which is the rest of them. 36 said yes, 26 said no, which is this decimal here. My pooled estimate just kind of lumps everything together. It lumps the number of successes together, 43 plus 36. We pool those together for 79. And then we total our numbers. We pool our numbers. 56 in that group, 62 in that group, adds up to 118 total. That creates a new fraction, 0.6695. And then Q bar, the easy way is just take that number away from 1, or take that fraction away from 1. So 79 said yes if you pooled them all together, which means 39 said no. And there's my two decimals. Remember, these two decimals always got to add up to 1 or 100%, however you like to think about it. Our challenge is that group 1's proportion is significantly greater than group 2's proportion. The null hypothesis is always, they're the same. There's no difference. All right. Our challenge is, hey, there's a big difference. Group 1 is a lot bigger than group 2. Now, why would I say that? Well, look at what our sample said. Our sample said, that's about 77%. Our sample said about 77% of conservatives said yes, and group 2 said, only about 58% of the liberals said yes. Well, 76% is more than 58%. I think I have a challenge here. So that's going to be our challenge. I took a sample and I took another sample. It looks like group 1 is a lot higher than group 2. That's what I'm saying right here. That's going to be my test. I want to see if it's high enough that somebody cares. I want to see if it's significantly higher. So we got to run the test. All right, here's our picture. All right, we want greater than. Greater than is shaded to the right. How much? You look at your alpha. Alpha level was 5%. I may have forgotten to write that down. No, I wrote it down. Alpha level is 5%. So this is 5%, this is 95%. Where do I draw the line? Look it up in the table or do it on your calculator. All right, so I'm going to draw the line 1.6 steps to the right. So 1 and about 6/10 of a step to the right. Shade to the right, that's 5%. That leaves 95% here. So 5%, if it lands here, I get to reject what they said. And if it lands over here in the white, I have to accept what they said. Next, you run your test. So we call it Z star, our test statistic. It's going to be our test dot. Plug in the numbers. You get 2.1599. That's just a little bit past 2 steps to the right. Here's 0, 1 step to the right, 2 steps to the right, and just a hair past it. Put a big dot there. That's where your test landed. And since it landed here in the shaded area, you win. You get to reject what they said. Their claim was the population proportions are the same. They're not that different. That's their null hypothesis. It's always going to be equals, no difference. You're going to say, yeah, there's a big difference. Group 1's proportion was significantly bigger than group 2's. My test statistic landed over here. I can say that, and I'm really, really confident that I'm correct. All right, so we reject the null hypothesis. I reject what you said. You said the two groups were the same. I ran my own test. I did my own sample, and group 1 is a lot bigger than group 2. Now notice the words are exactly the same. All right. If I'm rejecting what they said, that means I had enough evidence. That word's going to be is. If you can reject what they said, you had enough evidence at the level of significance, 5% in this case, to conclude that. And then the rest of it is just restate your challenge And you're basically just copying off the word problem. All right, and I'll let you guys read that. But higher than was my challenge. Group 1 is higher than group 2. You just want to kind of spell it out using the words from the problem. All right, then the last one I want to do, would you favor spending more federal tax money on the arts? That's the same question, but this time they asked women in group 1 and they asked men in group 2. They just want to compare the proportion of women who would spend more money on the arts with the proportion of men who would spend more money on the arts. Now, I haven't put my challenge there yet. I want to kind of work through it together. All right, in a random sample of 205 women, group 1, the number in group 1 is 205, 62 of those said, yeah, they'd spend more money on art. Group 2 had 162. The number in group 2 was 162 men. Out of those, 63 out of 162 said, yeah, they'd spend more money on art. Here comes our test. Does this information indicate a difference either way between the men and the women? All right, so difference either way, that just means not equal to. All right, we don't know if the women are going to be lower than the men. If I knew they were going to be lower than the men, I'd say less than. If I knew the women were going to be more than the men, I'd say greater than. If I'm not sure and I just want to kind of cover all my bases, I'll say, well, it could be lower, it could be higher. I'm just going to say not equal. All right, so the null hypothesis is going to say, just as many women would spend more on the arts as men. They'd say they're the same. All right, I'm going to say, no, they're significantly different. I'm not going to tell you one way or the other if they're lower or higher. I'm just going to say they're not the same. Here's our numbers, 62 out of 205. Remember, the true population proportion is unknown. We're going to guess at it with our sample numbers. 62 said yes. 62 women said yes. All right, this decimal right here. If 62 said yes, that means 143 said no. 205 minus 62 is 143. This is the rest of them, which is this decimal here. All right, men, 63 out of 162 said yes. So our sample is 63 out of 162. That's our proportion of success. 63 said yes. That means 99 said no. 162 minus 63 gives you 99. So 99 out of 162 said no, which is this decimal here. Remember Q, the easy way to find it is just 1 minus P. So 1 minus this gives you this, or 1 minus this fraction gives you this fraction. You can do that on your graphing calculator pretty easily. All right, our pooled estimates. All right, P bar is the number of successes pooled together. 125 said yes. Out of the total number of people, 367. So we pooled everything together and we got this new decimal here, this new proportion, 34%. So in our pooled proportion, 34% yes said yes, which means 66% said no. You just subtract it from 1. So if 125 said yes, that means 242 said no. 367 minus 125 gives you 242. So it's this fraction if you want to use the fraction, and it's this decimal if you want to use the decimal. All right. Null hypothesis always says, they're the same. There's no big difference. Your challenge is, no, there's a big difference. You're either going to say group 1's lower than group 2, or group 1's bigger than group 2, or group 1 in this case is just not the same as group 2. So they're saying the groups are the same. You're saying no, they're not. And you got to prove it that there's a significant difference. So let's draw our picture. Now remember, it's still 5% alpha. All right, alpha is 5%. Level of significance is 5%. That means I need 5% of the curve shaded. This is called our rejection region. So rejection region, rejection region. Now I can't put 5% here and 5% here because that would shade 10% of the curve. That's too much. So I got to take that 5% and I got to divide it by 2. I got to split it in half so that I have 2.5% here and 2.5% here. And we talked about that already. That's going to be the 196s. So if I take 1, 2, just short of 2 steps to the left and shade, that's 2.5% of the curve. And if this is 0, 1, 2, and just a hair short of 2, if I draw a line there and shade to the right, that's 2.5%. So 2.5% and 2.5% means 5% is shaded. So, all right, run your test. There's all your numbers from up above. You're going to come up with negative 1.74, let's call it. All right, so 1, and this looks like 0.75. Let's call that 3/4. So that's 1 3/4 steps to the negative, 1 3/4 steps to the left. Here's 0. There's 1 step to the left. There's 2 steps to the left. Whoops, I just want to go 3/4. Well, there's halfway, and then half of half is 3/4. That's about it right there. All right. So my test dot is 1.7 steps to the left, and my line is 1.9 steps to the left. You just have to kind of keep track of where you are. This did not quite go far enough to cross that line. This is 1.7 steps to the left. That's 1.9 steps to the left. We're a little bit short. We're close, but no cigar, all right? If it would have landed over here, we could say, you're wrong. You're wrong. I reject HO. I reject the null hypothesis. But it landed here in the 95% white area. So I lose. I have to say, okay, I accept your claim. I accept your null hypothesis that the two populations are roughly the same. I have to accept that. Let's say it the hard way. The hard way of saying you accept it is, well, I tried to reject what you said and I failed, which means you accept the null hypothesis. But most people say it the hard way. All right, interpretation of your conclusion. Notice the only words that change are is or is not. All right, I tried to reject and I failed. That means I did not have enough evidence at the 5% level of significance to conclude that, and the rest is just restating your challenge. Your challenge was that women are significantly different from men, with all the extra words that go with it. All right, that's it, guys.